In this chapter, we're going to look at benzene and aromaticity. And although there aren't a ton of reactions in this chapter, what we are going to look at is actual chemicals. So I'm going to use the writing a lot more than using the lecture notes in this chapter, although the lecture notes will be used to some extent as well, meaning the PowerPoint slides. So basically, I strongly recommend that you write these things down as we go. That doesn't mean copy everything from the PowerPoint slide down, but the stuff that I write on the paper, I strongly recommend that as you sit in front of a computer or a phone or whatever, you write that down as you go. Just like in the last chapter, I'm going to omit the homework from the videos, so you will be able to find the homework in the lecture notes that you can download. So here are the sections we're going to cover, 15.1 through 15.6. Okay, I'm not going to talk a lot about 15.6, and we won't do 15.7, which is the spectroscopy part, because we already talked about a little bit about the spectroscopy of aromatic compounds, whether you have a CH aromatic in IR, or you have the H proton of a benzene ring between 6.5 and 8 in NMR. So we've already talked about that to some degree, so I'm not going to get into the more nuanced details here just because, in the interest of time, there's a lot of material to cover. So aromatic compounds are very important, all right? Things like gasoline, petroleum products, are full of these aromatic compounds. So these are what we want to talk about. And like many of these chapters they start with naming. So aromatic compounds contain aromatic rings. And these aromatic rings have these alternating single, double, single, double, single, double bonds, and they're six-membered rings like this. What you're going to learn a little bit later in this chapter is that you don't have to have a six-membered ring to be aromatic. There are some examples of things that are not six-membered rings, which are aromatic. However, a common aromatic compound contains a six-membered ring, and this one that's just the six-membered ring is called benzene. If we add a methyl group to that benzene, we'd call it a toluene. If we add two methyl groups, we call it a xylene. All right, you can have two fused together. This is naphthalene, which is the stuff found in mothballs. If you have them separated, you may have used this in the lab. This is called biphenyl. And you can actually have three rings fused together, such as in anthracene, or if it's a slightly different orientation, phenanthracene. So these are... this is phenanthrene. So these are just some examples of compounds that contain aromatic rings, but there are lots and lots and lots of compounds that contain aromatic rings. And as I mentioned in this first section, what we're going to look at is these names. All right, so these are some common names that I do want to point out a few of them because they do come up. So some of them are straightforward. Some of them are, a little bit, you kind of have to memorize them. So here we have toluene, which is a methylbenzene. This is a common solvent used in an organic chemistry lab. Here we have phenol, which is a hydroxybenzene, if you will. It's a benzene with an alcohol OH. And if you have an amine, we call that aniline. So an amine attached to a benzene ring, we call that aniline. This one is pretty straightforward. We have acetophenone, which is a ketone, right? This would be acetone if this was a CH3 on this side, but because there's a phenyl group on this side, a benzene ring attached to another group is called a phenyl group, which we haven't talked about yet, but that will come up. This is called acetophenone. Benzaldehyde is fairly straightforwardly named, right? We have a benzene group attached to an aldehyde, C double bond O bond H, so benzaldehyde. Benzoic acid, same thing. We have a benzene ring attached to a carboxylic acid, so we call that benzoic acid. Xylenes, all right, this particular one is orthoxylene, but you could also have metaxylene and paraxylene, and we'll talk about the ortho, meta, and para nomenclature in just a minute. And then styrene, this one is used in polystyrene, which if you blow air into it is then called styrofoam. So these are some different examples. You don't need to memorize all of these. I just want to point them out because they do come up, right? You use toluene in the lab. Occasionally we use phenol in our organic chemistry lab. Aniline comes up. It's a solvent. Benzoic acid I know we use in the lab as well. So these different compounds form with benzene as the central structure, if you will. So what I'd like to look at now is, well, what happens when the benzene isn't the predominant force in the naming. So let's look at an example here, or actually two different examples here. And the first, we're going to have a benzene ring. Note that I draw mine with a circle in the middle instead of alternating single and double bonds. Sometimes I will draw it with alternating single and double bonds, namely in a reaction mechanism, because that becomes important for understanding the reaction that's going on, but it's easier to just draw the circle in the middle, and this indicates a benzene ring. And we could have attached to this a CH2, CH2, CH3. Or we could have attached to this a CH2, 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 that's 1, 2, 3, 4, 5, CH2, CH3, 6, and 7. So in this case, this benzene is considered as the predominant structure because it has 6 carbons, and this group off of it has only 3 carbons. So this could be called propyl benzene. All right. And propyl means 3 carbons, right? So this would be propane if it was just CH3, CH2, CH3, but because it's sticking off, we call it propyl, attached to a benzene, propylbenzene. In this case, we have 1, 2, 3, 4, 5, 6, 7, which you think would be called heptyl, right? Because heptane is 7 carbons, heptylbenzene. But in this case, we actually, because this has more carbons than this is considered the predominant structure. And instead of calling this propylbenzene, we call this phenyl heptane. Probably 1-phenyl heptane is a better name. So in this case, we use the benzene as the predominant structure. In this case, we use the benzene as the not predominant structure, and we called it phenyl. Do I care if you know that if it's 3 carbons, you name it this way, and if it's 7 carbons, you name it this way? Not really. But what I do care that you know is that if it has benzene in the name, it's got this ring. If it has phenyl in the name, it means it has this ring attached to something else that's been determined as the dominant group. So these terms are important to know. Whether you use them in one case or another, the truth of the matter is that, you know, it's not always easy to tell, okay, which one you should use. I mean, technically, if you have more than 6 carbons, you should use the phenyl nomenclature. But what if you have 2 phenyl groups, right? This kind of stuff. Usually if you have 2 phenyl groups, they are called phenyl. So again, not super important that we know which one to use. What is super important is that we know if it has benzene, it's got a ring in it. If it's got phenyl, it's got a ring in it, okay? So the other thing to note is that we don't always have these mono-substituted rings. And before, we looked at some common names of these mono-substituted rings, like things like phenol, where you have an OH on there, or aniline, where you have an NH2 attached to the ring. Sometimes we have more than 2 carbons attached to the ring, or more than 2 groups attached to the ring. So this leads to new nomenclature that we actually already mentioned before but didn't discuss in detail. So let's look in a little bit more detail. So I'm going to draw here. That's not a very good one. So I'm going to redraw. It's a shame I don't have an eraser like I would on a whiteboard. But I'm going to redraw my phenyl ring. So let's call this something attached. We have X attached, so our first group is here. We're not going to worry about what this is. Now, what we're looking at is the relation to this group. Well, it could be 1 carbon away on either side. Remember, we're looking at di-substituted benzene rings, meaning there's only 2 substituents. In a few minutes, we'll look at more than 2 substituents on the rings. But here we're only looking at 2. So it can be 1 away on this side or 1 away on this side. This and this are called ortho, sometimes abbreviated as just O. And this one's also ortho, or just O. All right. What if we're 2 carbons away? So 1 carbon, 2 carbons away, here or here. These are called meta, which is, not surprisingly, abbreviated sometimes as just M. And this one is meta, or just M. All right. And then finally, down here, and there's only one of these possibilities, we have para, which is sometimes abbreviated as P. So we can have ortho, meta, and para substitution for two substituents on a ring. So let's look at three examples of this. And the three examples of this we're going to look at are dichlorobenzenes. All right, to keep it simple, so we don't need to know the phenol nomenclature and stuff like this, we'll use dichlorobenzenes. So the first chlorine in all three cases will be there. All right. And in this case, the second chlorine will be there. In the next case, these have long names, so I need to space these out. Okay, we have this, and we have our first chlorine here. That's a chlorine. And our second chlorine here. And in our last case, we have this spread out, and we have one chlorine here, and we have one chlorine here. Now, if we were doing this as a class, I would say take a second and write the names of these three things. So let's look at the first one, okay? And we need to just determine if it's ortho, meta, or para. So I've conveniently written the first chlorine to the top. You don't necessarily have to do that, right? It's how far apart they are from each other. It doesn't matter if the first chlorine is at the top, and I'll show you an example of that in a second. So if you have this one, and you have this chlorine at position 1, this is 2 and 3, 1, 2, and 3, or 1, 2, and 3, either way, you get meta, or M, dichloro, benzene. Okay? Note that there's another way I could draw meta dichlorobenzene. If I wanted to redraw this, and for whatever reason I wanted my first Cl to be there, I can now draw my second one meta to this. 1, 2, I could draw it here, or 1, 2, I could draw it here. And if it was here or here, these would also be meta. It doesn't have to be that the first one's at the top. It could be anywhere. Okay? So this is basically the same thing. If you think about it this way, if you turn this 1/6 of a full rotation, it would look exactly like this. All right, let's look at the next one. So we have a chlorine here and a chlorine here. So this is at 1, 2, 3, 4. 1, 2, 3, 4. This one is para, or P, dichlorobenzene. All right, and this last one, you guessed it, it's ortho. All right, it's 1, 2. Well, this is the only one that's left. 1 and 2 is ortho dichlorobenzene. So these are three examples of ortho, meta, and para dichlorobenzene. So let's look now at a real-life example that I looked up on NIST a few minutes ago. All right, National Institute of Standards and Technology. So if we look here, this is 2-methylphenol. So in this case, we called this OH group phenol. And now we have a 1,2 position, which is 2-methylphenol. You'll notice that there are other examples of what it could be called. And the interesting one is O-hydroxytoluene, which is ortho, or 2-hydroxytoluene. So you'll see that these nomenclatures aren't always used, but they're used enough that you have to know what they mean. Okay? So 2-methyl means 1, 2, and because this is phenol, that means the OH is at carbon 1. But people are also calling this O-hydroxytoluene. If you recall, toluene is with methylbenzene, and they're calling the OH a hydroxy group, and they're ortho to each other. So another name of this is orthohydroxytoluene. The point of this is that even though there are accepted formal ways of doing these things, people don't always use them, and you have to know the basics to know what people are talking about. So what are the basics that we have to know in this case? Well, the basics that we have to know in this case is we could call this either a phenol or a toluene based on the OH or the CH3. We could also call it 1, 2, or we could call it ortho. Note that if we call it a toluene, we defaultly make the CH3 as the 1 position. So this is 2-hydroxytoluene. If we call it a phenol, which is using the OH, then we have 2-methyl-phenol. So this makes the methyl group at carbon 2, or defaultly makes the OH at carbon 1. So if you call something aniline, okay, the NH2 is defaultly at the 1 position, and then you could say, it's 2 or 3 or whatever. If you use the orthopara nomenclature, it's not so important because then there's a relative distance between them as opposed to, using absolute numbers of one thing being 1 and one thing being 2. Again, are you going to be asked to name this and you're going to be, this is the right answer and these are the wrong answers? Not in a million years. That's not the point of this. The point of this is knowing the ortho, the meta, the para nomenclature. It's knowing the toluene and the phenol nomenclature. And it's realizing that all of these things are different ways of expressing these aromatic rings. And again, there is probably a technically correct one, but we're not worried about that here. All right, so the next thing that I want to talk about is, well, what if you have more than one substitution? All right, so we looked at di-substituted rings. What if we look at tri or tetra substituted rings? So the example that I'm going to give here is, let me make sure I'm on the screen here. Come down a little bit. All right. All right, so we have a C double bond O bond OH. This is a benzoic acid. And let's say that we have a bromine here and a bromine here. All right, now the ortho-meta-para nomenclature doesn't work very well because we have multiple substitutions. But you've already seen what is going to work. The 1, 2, 3, 4 nomenclature using numbers instead of using letters. All right, so how are we going to do this? Well, the first thing I'm going to do is I'm going to decide what to call this. All right, and I'm going to decide to call this benzene with a carboxylic acid. So I'm going to decide to call this benzoic acid. As soon as I call this benzoic acid, that makes this carbon 1. Because my name is based on this functional group. It's based on the fact that this is a carboxylic acid attached to benzene, which if you remember from the slide earlier, is called benzoic acid. Now I have to decide where are my 2 bromos. It's going to be a dibromo benzoic acid. So I can actually even write that in because they happen to be the same functional group. So we have our dibromo benzoic acid. You don't need a space there. All right, it's just hard to write here and space it out properly. All right, so we have 1, 2, 3, 4 before we get to the first one, or 1, 2 before we get to the first one. If you have 2 before you get to the first one, or 4 before you get to the first one, you have to pick 2. Said another way, I have to number in the clockwise direction. I can't number in this direction because if I numbered in this direction, it'd be a 4, 5. 1, 2, 3, 4, 5, 6. A 4, 6 dibromobenzene. I have to number it the other way. 1, 2, 3, 4. So I have to call this a 2, 4 dibromobenzoic acid. All right, so that is how I would name a tri-substituted ring. So the last thing that I want to do here is I want to draw from the names 3 things because we've done several examples where we've named something, given a picture. Now I want to do the opposite, given a name, draw a picture. Okay, so let's have this one, draw, and I'm not going to write draw every time because we're going to draw 3 of them. All right, P chloro benzaldehyde. All right, so we want to draw p-chlorobenzaldehyde. So the first thing we want to do is draw benzaldehyde. Benzaldehyde is a nice descriptive one like benzoic acid. So benzaldehyde means aldehyde attached to a benzene. So aldehyde is C double bond O bond H. All right, so it's got an H on one side, a carbon on the other. This is an aldehyde. P-chlorobenzaldehyde. P means para. Remember, ortho, meta, para. There's only one para group. In this case, it's a p-chloro, so we put the chlorine at the bottom. This is p-chlorobenzaldehyde. All right, next one we want to draw is 2,4 dichloro phenol. All right, phenol is kind of one of those ones you have to memorize because it's not as straightforward, but it does end in OL. So a phenolic alcohol or a benzene ring attached to an alcohol. So here we have our phenol. All right, so that's what we have. Now we need to make it a 2,4-dichlorophenol. Note that when we're doing it, we can decide which way we want to go. Do we want to make this 2 and then continue to make this 4? Do we want to make this 2 and continue to make this 4? It makes no difference, all right? I like to go clockwise for whatever reason, but it makes no difference. So in this case, at the carbon 2, I'm going to put a chlorine. 1, 2, 3, 4. At carbon 4, I'm going to put a chlorine. And this is my 2,4-dichlorophenol. The last one is O-nitroaniline. All right, or 2-nitroaniline. We use this one in the lab in a chromatography experiment because it's a yellow color. All right, so let's go ahead, draw our benzene ring. We need to remember that aniline is an amine attached to a benzene ring. Said another way, it's an NH2 attached to a benzene ring. We now need ortho. Remember, ortho, meta, and para. So for ortho, we need to go 2 carbons over, and we need to draw a nitro group, and we need to be aware that a nitro group is an NO2. So we've now done both types of examples. We've gone from a structure to a name, and we have gone from a name to a structure. These are the 2 types of naming that you can really accomplish, right? In the next section, we'll start to talk about why benzene is a particularly stable molecule. And there, the next couple sections are more descriptive, and there'll be a little bit less of the notes over here.